Hello, everyone. We are so pleased that you are all joining us, and we are incredibly fortunate today to welcome Dr. Daniel P. Raymer as our master lecturer. As you all know, the GoFly Prize is sponsored by Boeing. Boeing is our grand sponsor. And we are also joined by several international aerospace and engineering organizations around the world, including the Vertical Flight Technology Society, AIAA, AOPA, EAA, AUVSI, SAE, GAMA, the Royal Aeronautical Society, 3AF, ABCM in Brazil, AIA, ASEE, AMIE, and Great Minds in STEM. We are so very pleased to welcome Dr. Daniel P. Raymer today. Dr. Raymer is president of the design and consulting company Conceptual Research Corporation and is well renowned as a blank sheet of paper aircraft conceptual designer. He is an AIAA Fellow and a recipient of the prestigious AIAA Aircraft Design Award. Dr. Raymer is recognized worldwide as an expert in aerospace vehicle design and configuration layout, computer-aided design methodologies, and design education. Dr. Raymer is author of the world's best-selling book on aircraft design entitled Aircraft Design: A Conceptual Approach. And he teaches aircraft advanced design methods around the world. And so without further ado, join me in welcoming Dr. Daniel P. Raymer as our master lecturer today. Thank you for joining us.
Well, give me just a second to get the right screen up here. Go. Okay, I think we're good to go. Hopefully you're seeing my first slide. Nice to be here. Actually, here is in my office, and for some reason I'm wearing a tie in my own office. That's unusual. Anyway, I was asked to give this first talk for the GoFly Prize and participate a bit in the prize activities, and it's a very exciting thing to be involved in. And I was asked to give kind of an overview on conceptual design and some of the things that might impact this particular activity. So I pulled some material together from my aircraft design textbook, which some of you may be familiar with, and also the short courses that I teach on aircraft design. I normally teach a 5-day in-depth aircraft conceptual design short course, and I pulled some material for this talk. Of course, I can't go into much depth here, but at least I can give you a flavor of it. Let me point out one thing. There is this, I think, rather cool looking airplane here. I did this for a little activity a couple of years ago and did an AIAA paper on it. But I just want you to know that that's just eye candy. That is not my suggested design. In fact, that design doesn't meet the requirements. So it's just pretty. Okay, well, let me jump right into it here. First of all, the requirements. There is already a complete detailed lecture on the requirements alone, but I thought I'd run through it briefly as it affects aircraft conceptual design. So here they are. Forgive me for looking down, but I have to look down to read my own screen. Anyway, basic idea, this is supposed to be manned, okay? You know, I know a lot of people will fly it unmanned for the contest, but the intent is a manned aircraft, and it would be totally cool to actually fly it manned, but not required by the rules. The target weight is 200 pounds, including the parachute. Now, I weigh 200 pounds. I weigh more than 200 pounds without a parachute. So I'm kind of hoping that your vehicles can carry more than 200 pounds because I want to fly them. So you might up that to 220 or 240 for a really big guy with a parachute and everything else. But again, the rules say 200 pounds. I will point out, by the way, this is my own summary, not the official rules. If there's a conflict between what I say and the official rules, of course, official rules are more important. Very interesting is that it is a VTOL design. Well, not really. It's got to take off and land within a 30-foot diameter cylinder 12 feet high, which makes it very difficult to do any kind of a rolling takeoff. So probably VTOL, although certainly if you can think of a way to do it, go for it. 30 knots minimum speed. It's got to go at least that fast. That's kind of funny. I would see that and think that's a really low stall speed. No, that's That's the minimum number for the fastest speed. You have to hit at least that speed. And of course, faster is better, especially if you want to get some reasonable range out of this thing. Also consider the fact that if you're a pilot, as I am, it's not uncommon to have 30-knot winds in your face. So if you have a 30-knot speed and a 30-knot wind in your face, it's going to take you a long time to get there. The actual competition is laps around a pylon, something like a 20-minute flight or so, but you'll probably be making a big oval around the pylon. Noise limit, that might be the toughest, actually. There's a whole lot of vehicles out there that could probably do this sort of thing. It's not that far off from what we can do, but doing that within the noise limit is going to be tough. That's about the sound of a lawnmower, and it's right at the ragged edge for permanent hearing damage. So you probably want even lower than that. There is a maximum dimension. It's 8.5 feet. People think, oh, that means a circle. No, if you actually look at the way they wrote it, it's really shaped like a guitar pick, and I happen to play guitar, so here's a guitar pick. So that kind of a shape actually is the absolute contest minimum. So maybe you want an airplane that looks like a guitar pick from top view. Probably not. But in any case, that is within the limits. There's a detailed requirement for field of view. Basically, though, it means you have to have a good field of view. Okay? Down at the bottom, there's existing vehicles that can either do this or can come awfully close to it. So this isn't an existence proof. This isn't the first man-powered airplane or something. It's more of a race. So if you want to win the race, check the scoring rules very carefully and optimize your vehicle against the scoring rules they came up with, rather than perhaps against your own vision of what this ideal vehicle should be. But the scoring rules, I think, are pretty well thought out. Okay, well, let me talk about the whole vehicle design process a little bit, and then I'll go into a couple of details here and there. First of all, we start out with the requirements, and I just talked about them briefly, and we'll normally take customer inputs like that, and we'll also try to come up with maybe a little bit more detailed, a little bit more subtle requirements to guide our own design process, like what we think a reasonable customer would want in addition to whatever the hard and fast rules are. So you can get customer inputs as shown here. There's a funny acronym we used to use at RAND Corporation when I worked there, BOGSAT. Stands for a bunch of guys sitting around a table. That's actually a pretty good way to work through requirements. If you have a number of people who each kind of know what they're doing and different backgrounds, you can come up with some pretty good input before you start. Down at the bottom, information gathering. Of course, you don't jump into something like this without getting a whole lot of information. And try to be broad also. Try to really understand what other people are doing, what other potential answers might be. But you need the hard numbers too. You need to find out what engines are out there and propellers if they're existing and tools, batteries if you're going to go the electric route, all that sort of thing. Okay, well then you go into a conceptual sketch process. We do a lot of that. It's kind of fun. You look like you're just sitting there having fun scribbling things on a piece of paper. But you're really trying to sort through the different design alternatives, figure out where the big pieces might go. Once you have that, then you need a quick estimate of the vehicle weight. You sort of can't do the drawing, you can't do the design layout without knowing how much the thing ought to weigh, because you have to size the engine, and the engine size is based on total weight. You have to size a wing if you have it. You have to size the rotor if you have one of those. They're all based on the total weight. So we sort of make a quick guess, and then we come back and iterate it later. That's an integral part of the design process. So how do we come up with this quick vehicle weight? Well, one of them is actual mission sizing, and I'll talk about that in a few minutes. The second one is simply estimating what the thrust-to-weight ratio has to be and picking an engine. And kind of instantly find out what the weight would be. Or you can do it on a power basis, finding power loading. Or another acronym we used to use, TLAR, stands for, that looks about right. And we do that a lot. I've been doing this a while, and when I started in design, I usually don't take out my pocket calculator and do quick numbers anymore because I kind of know what looks right. But if you're new to this, that's good to go through these processes. Okay, well, then we take that information and we make a real layout. And I'll talk about that a little bit later, but it's the overall external geometry. Usually these days it's in some kind of a CAD system. We usually look at side, top, and rear view because they're very informative to us. We make sure the things fit, take a lot of cross sections, make sure it all fits, put the layout together, do some analysis, trade studies, and optimization. When you do that layout, you need some information and you need some tools. So you do have to have a good set of tools, something you have to think about. If you have access to a high-end CAD system, great. or perhaps a CAD system developed for air vehicle configuration layout, which is what my own RDS software does. Aerodynamic tools, classical methods, or computational fluid dynamics, structure tools, finite element, even simulation, 6 degree of freedom, all that kind of stuff. The more tools you can get, the better, as long as you know how to use them, and as long as you know what answers should look like, so you don't wind up thinking something stupid is the right answer to 12 decimal places. Hand calculations can be fine also if you know what you're doing. Good pocket calculator and kind of textbook, handbook methods. And at the very least, they're very good for checking the answers you get out of the fancy tools. And finally, at the bottom here, yeah, you need some skills and experience. And you better sort of check the team and see who knows what, and maybe bring on some other people if you don't have all the total skills necessary. Okay, so you develop a configuration, as I said. You iterate that. You do the analysis. You come up with the range. It's not the right number. So you change the design, usually make it bigger to meet the range if you're not meeting it yet. It's very normal to iterate through the design. You never build that first drawing you make. In fact, usually you wind up 10 or 20 different iterations before you finally start to settle in on hopefully the right answer. I'm working a major project right now. Can't tell you anything about it, but what I'm doing right now is iteration number 7. Those of you that are on it know what I'm talking about. I was on a project years ago. We got up to iteration number 100, and then it was canceled. Okay, so you iterate through, you come up with a final design, hopefully. You do a final analysis, and this is in more and more depth. You get into detailed design of structure, subsystems, and all those sorts of things. So that takes you to, hopefully, your final frozen design, the one you're going to build. You need to start bringing in the kind of people who can actually build the thing if you don't have them on board already. Actually, a good idea to get them on board on the first day. You have to identify where you're going to build it. You have to design all those parts. And what does it take? It takes money and time. Okay, let's see. Trying to get to the next one. Let me talk a little bit about some of this vehicle sizing stuff. So there's a couple of ways of doing that. The normal way in aircraft design, the normal aircraft sizing process is based on burning of fuel. And as you burn fuel, the aircraft gets lighter. And basically, there's an integral way of coming up with an equation that tells you the answer. A guy named Breguet a long time ago figured this out, did a lovely little sneaky integration. If you're interested, it's in my book and all the other books. It tells you the range based on burning fuel, and we work that and come up with a way of actually sizing the airplane. So sizing is trying to calculate how big the airplane has to be. And when I say big, I mean weight. So you're calculating the takeoff weight required to meet some mission requirement, some range, some payload, some endurance, whatever else you might have. And of course, for this project, it was given primarily as endurance, but you also have to meet a range requirement. So here's how we do it. Very simple equation. The W0 is the takeoff weight of the airplane. It's the crew weight, payload weight, fuel weight, and empty weight. Kind of adds everything up. The empty weight, by definition, is everything that isn't crew, payload, and fuel. So the empty weight includes structure weight, propulsion, all the equipment inside. Everything is in empty weight except crew, payload, and fuel. So what we do to make this easy to solve is we define a couple of simple ratios, a fuel fraction shown here, an empty weight fraction here. It's a ratio. And once you define those fractions, high school algebra will let you solve for it real quick, and you get this equation down here. So you can calculate takeoff gross weight from the weight of what you're carrying up here in the top, 1 minus fuel fraction minus empty weight fraction. So what we have to do is come up with credible estimates of those. And yeah, that takes a lot more time. I can't really talk about it all in this limited amount of time. Obviously, it's in books, not to mention any particular one. So that's the main equation that you wind up using. The fuel fraction comes basically from engine characteristics, the drag of the airplane as you design it, and the mission itself, how far you have to go, the endurance, et cetera. And it's a mathematical process, and you find out a fuel fraction. The empty weight's a little more tricky. Oops, wrong button. Sorry about that. Didn't know it would do that. Okay. The empty weight is much more difficult because you have to add up all the parts, and we haven't even drawn the vehicle yet. So what we normally do is statistics. So we get data on a lot of similar vehicles. We make a plot that looks like this. The horizontal axis is the takeoff weight. Vertical axis is that fraction, empty weight divided by takeoff weight. And you see this characteristic trend. It kind of goes downward. So a heavier weight airplane almost always has a lower fraction of empty weight than a lighter airplane. So that's what we do. But if you look at all my lines here, none of my lines are a vehicle that matches the Go Fly Prize Challenge. So it's kind of your problem. Sorry about that. Very difficult to do statistics of something that's really quite new. But you can get data on all the similar vehicles you might find that are anything like what you're thinking of doing, and plot them on this and draw your own line and use that for this estimation. Okay, well, that's what you do roughly for an airplane in which you're burning fuel. What about an electric aircraft? Electric aircraft, you're typically not burning any fuel. Obviously, you've got a battery, and an empty discharged battery weighs the same as a full battery. Actually, not exactly. A guy named Einstein calculated how you can find the weight difference, but it's not a big number. So for our practical purposes, yeah, they weigh the same. Even something like a fuel cell electric vehicle, the weight of the fuel itself, the hydrogen or whatever, is very trivial compared to the weight of the aircraft. So you basically need to find a way of calculating the weight of an airplane that isn't changing weight during the flight. Sounds easy, it's actually kind of tricky. Most of the time, what we do is we work backwards. At least this is what I usually do. I actually make that rough guess of takeoff weight from a selected power loading, weight divided by horsepower to give me performance I'm looking for. I select a candidate motor, and that allows me to quickly calculate a takeoff gross weight to reach this ratio. And then I lay out the airplane based on that and calculate the weight of all the components and whatever's left over. I take the takeoff weight and I subtract all the other weights. Whatever's left over is battery weight. So I stick in that many pounds of batteries, and then I can calculate how far it goes. And if it doesn't go far enough, yeah, okay, I have to pick a larger airplane and go through the process again, come up with a different motor that's a larger motor, work backwards, et cetera. So it's an iterative process. So you make a bunch of quick calculations. You don't do a full detailed layout until you think you have the answer. There is an analytical approach if you want to take a look at that. It's a bit more complicated. I won't talk about it here. Martin Hepperl came up with, I think, a rather good paper on this, and I highly recommend that for you, actually. I found it online as a PDF, and it's got lots of good stuff in it. Okay, that's the analytical approach. Now, when you do an electric vehicle of any kind, though, the big problem is that battery. And I hate to break the news to people that aren't aware of this, but they're not that good yet. We're a long ways from batteries that are competitive with a tank of gasoline. Even when you take into account engine efficiencies and drivetrain efficiencies and everything else, a tank of gas is something like 20 times better in energy density. And that's what's shown here on this graph. The blue one over here is a tank of gasoline after taking into account the energy efficiencies and everything else. This was back in 2002, and perhaps it's a little bit better now. Here are some newer projections. But nevertheless, we're still pretty far away, although we keep getting better and better. And people estimate roughly somewhere around 1,000 watt-hours per kilogram will probably get you to the point where a battery-powered vehicle really is competitive with a gasoline-powered vehicle in terms of speed and range and all those sorts of things. And if they can make it so it charges quickly, that will be fantastic. It's very easy to pour a new tank of gas in. So that's fantastic. The biggest problem with that is going to be as you increase power density, your battery looks more and more like a bomb. So that has to be solved also. And do be careful about college professors and research laboratories quoting these watt-hours per kilogram, because a lot of times they don't include all that real-world stuff that's necessary to make it something you can actually put in a flight vehicle. So it's coming. It really is coming, but it's not where we'd like it to be yet. Okay, well, let's see a few more things. We were talking about this overview of the process, and let me talk a little bit about estimating these thrust to weight and power loadings. So just a couple of things again from my aircraft design short course. So we need to estimate thrust to weight ratio, and if we are flying on wing lift during cruising flight, if you're going to try to get a decent cruise speed out of this vehicle or anything similar, turns out there's a very easy way to calculate the required thrust to weight in cruise. We take simple equations in cruise, thrust equal drag, lift equals weight, and smush those equations together and you get a neat result. Thrust to weight is just 1 over the lift to drag ratio. So if we can estimate L over D, say we get a number of 20, 1/20th is the required thrust to weight ratio. That's a small number. Now in climb, you need more thrust to get it to climb. So we have a little bit more complicated equation where these are the components of weight And we smush those equations together, and it turns out to be a pretty neat equation also. 1 over the lift-to-drag ratio again, plus the sine of the climb path angle. And that's just the desired vertical velocity over the vehicle velocity. So we can actually calculate the thrust to weight required for climb also. That's pretty easy to do. What about that lift-to-drag ratio? Well, the right way is good aerodynamic calculation codes. Here's a quick way. If you know the span and you know the wetted area, you can get a pretty good approximation with this chart. You just divide them and come in here and go up there and read over. So that's, you know, a quick number to get you started. What about power? We can take the power divided by the weight of an aircraft. So we can call that a power-to-weight ratio. And we can calculate a thrust-to-weight ratio from the power-to-weight ratio. We'll talk about efficiency in a minute. So that's what you would imagine using. It's kind of equivalent to a thrust-to-weight ratio. But for historical reasons, they came up with something they call power loading, which is the inverse of a power-to-weight ratio. So power loading is the weight of the aircraft divided into the horsepower. So it's kind of weird. It's backwards. A big number is a little engine. A little number is a great big engine. But this has been used for a very long time. So down here are some typical examples, everything from powered sailplanes with a little tiny engine, so it's a big number, 25, all the way to twin turboprops, regional type airplanes, and they have a small number, so those are very powerful engines for the weight of the airplane. Helicopters are actually not even that powerful for civilian ones. They're around 8 or so horsepower, 8 or so pounds for every horsepower. Military helicopters that are chasing and fighting bad guys have much more power, as you'd imagine. So they're up close around 5. So these are actually reasonable first numbers to use as you're doing that initial layout. And let's now talk about calculating wing size and things like that. Forgive me for blasting through all this stuff so quick. I'm trying to give you a flavor for what takes a week to learn and a lifetime to master. So forgive me on that. If you are flying with a wing, and some of the candidates probably won't, but if you are flying with a wing, then you want to make sure the wing doesn't stall. If you're trying to make your takeoff with wing lift, well, I don't know, that's going to be an awfully big wing if you want to get off the ground and clear an obstacle within 30 feet. So I don't know if that's going to happen. But on the other hand, you might take off some other way and transition to wing lift for forward flight, which is going to be far more efficient. So in any case, you need to calculate the wing size required to meet a particular stall speed. So we just set the equation weight equals lift, and this is the dynamic pressure, wing area, and lift coefficient. And it's very standard equations that get in an early introductory aerodynamic class. So down here are some typical values to use. The most difficult one to find is this maximum lift coefficient. So here's an old chart I've been using for years. I think it's Boeing data from a paper a long time ago. And it gives you a rough idea of the maximum lift coefficient. So if you have a simple wing like a Piper Cub with no flaps or anything, and it's a straight wing, yeah, you're going to get a lift coefficient, a CL max of about 1.5. Not very good. Put all kinds of fancy flaps on it, you might double that, but fancy flaps aren't free, and they have a whole lot of drag. Now, if you have the whole wing in the wake of some kind of propeller or rotor, like this funny little design I did, then you can get insanely high lift coefficients, and it's almost fictitious. A lot of this apparent lift is really actually the thrust of the engines themselves at a high angle of attack. But yeah, you can get 10 or 20 or even more if your whole wing is buried in a flow field like that. Okay, if you're taking off purely on vertical lift, well, a couple of things to consider. It isn't enough just to say that your thrust equals weight. You need more than that. Here on the left is actual data for the Harrier, which is, of course, this jet here on the right. And that's a jet, so it's a little bit worse than what I'll talk about for propeller and fan type vehicles. Okay, but thrust has to be more than weight. You have to be able to accelerate upward, so you have to go up when it's time to go up. And the normal helicopter requirement is about 5%. So you need thrust of 1.05 times the weight in order to accelerate vertically. Very typical helicopter number. Otherwise, you don't get off the ground very quick. The wind blows you sideways into things. It's just not safe and doesn't feel right. Whenever you're hovering, you're also blowing air downward, though. So you have to watch out for that. The air blowing downwards literally pushes down on the vehicle. If you have a helicopter underneath the great big rotor, it's 1, 2, maybe 3% of the lift is lost because of this pushdown force. For a jet-powered aircraft, you get something very similar. The jet entrains air. In other words, the free air out there kind of gets pulled along, sort of goes for the ride, and it winds up pushing down also. So you have to take that into account. And there is one possibility, though, and that's a fountain lift. As that air blows downwards, it can hit the ground, turn around, and come back up. And that's what the Harrier does right in here. It actually has 4 nozzles, 2 on each side, and they hit the ground, and it comes back up in the middle and literally pushes up in the center. So you can take advantage of that if you're very careful. But then when you get higher up, of course, you kind of lose that. So anyway, you need more than just thrust equals weight. I think probably about a 10% margin is probably reasonable. Maybe even more if you're not real sure what exact thrust you're going to get, because you sure don't want to build your vehicle and wind up with a little bit less thrust than needed for takeoff. It's been a long time since that happened. We don't want to repeat that mistake. If you are looking at a jet lift engine of some sort, I don't know if anybody is, but it certainly isn't impossible. There's even more losses from hot gas and control effects. So just be aware of that if you decide to do a jet engine. All right, well, let's talk about how much power it takes to get enough lift for that vertical takeoff. And this is an old chart. In fact, I stole it from somebody else. I forget who. I think it was a McDonnell Douglas report a long time ago. All of these little blobs here are blobs that I stuck on top of real data. There's hundreds of points for this actual chart. So this is real data, even though it looks like blobs. So you can see the thrust you get per horsepower in hover, and it changes by a factor of roughly 20. So literally, a great big rotor up here gets something like 20 times as much thrust as a jet like the Harrier with the exact same power applied. So obviously the answer here is low disc loading, big rotor, as big as possible for efficiency. But of course, then you have to drag that thing around in forward flight. And don't forget your 30-foot diameter takeoff limitation. So you have to worry about that. There's also a problem as you go to a higher disc loading more to the right, and that is the velocity of the air has to go up. To get the same thrust from little rotors like this compared to a big one like that, you need to push the air a lot faster. So over here, I've got the Harrier. It's a jet engine. The exhaust is coming out at just about the speed of sound, aimed straight downward. You don't want to be under that. It will kill you and fling your body hundreds of feet in the air. So you don't want to do that. Whereas these big helicopters, you can literally stand under them and wave at the pilot and no real problem. It's just blowing down on you. So a long time ago, the Army came up with a rule of thumb, and they said for their helicopters, they don't want it to be any worse than about 10. And that would be awfully nice. You can stand under a disc loading of 10 when it takes off right over your head. Vehicles like this, V-22 and this test vehicle beforehand, they're quite a bit higher. I forget the number, it's 30 or 40 or something. So you can stand under that when it takes off, but it's a lot of wind blowing on your head. Much past that, you don't want to be under it. Okay, so that's kind of the top level view of vertical takeoff. Let me talk about propellers themselves. What does a propeller actually do? We often say it wrong. People say a propeller, that's supposed to be a propeller, turns power into thrust, and that can't be right because the units are wrong. If you look at it as a physicist, that just can't be right at all. That'd be like turning inches into degrees centigrade. I mean, it's just not possible. The units are wrong. So you have the apples to oranges problem. That can't be right. So what's actually happening is this. A propeller is turning power into power. It's turning one form of power into another. So it's turning shaft power, P, into thrust power, which is thrust times velocity. And if you look at that and think about it for a second, there's an obvious, interesting problem. The engine puts out a fixed amount of power, and that is equal. So the right side is not changing. So if the velocity is higher, the thrust is lower. And that's the real reason that propellers aren't very good at high speeds. It's this fundamental physics. Okay? The opposite is true, though. If you're flying at a lower speed, velocity is low, so the thrust is much higher. So if you fly at a really, really low speed, you get tremendous thrust out of the same amount of power. Now, unfortunately, propellers aren't perfect, so they lose some of the power, so we apply a knockdown factor. We call it A to P propeller efficiency. It's a knockdown factor. It's the propeller saying, oops, sorry, boss, I lost, and the typical number is 20%. So typically A to P is 0.8, the propeller loses 20% of the thrust. If I take this equation now, I can solve for thrust and forward flight. Looks like this: power times that knockdown factor divided by velocity. That knockdown factor, you can use 0.8. We can get propeller data from charts. It's a bunch of test data, looks like this. Or you can write a computer code that'll estimate that for you. The Wright brothers actually developed some equations. They were one of the first to develop an actual propeller thrust model. And that's one of the reasons they wound up successful. Their propeller was so much better than everybody else's. Okay, well, anyway, if you look at this equation, that's how you calculate thrust and forward flight. Here it is again. But what happens when that velocity term is zero? Well, if the velocity term is zero, well, it's mathematically undefined. The thrust is trying to go to infinity. So something funny happens, and what happens is the math, the physics is wrong. And the reason it's wrong is because there never is actual zero velocity at the propeller, because the propeller pulls air into itself. That's why we put a propeller on our desk on a hot day. It pulls air through itself and blows it on our face. So same story. So the people that design helicopters have rewritten the equations to take that into account. I won't go over it here, complicated equations, but when you're all done, it's a nice equation. Or here's a nice approximate out of a good book by a guy named McCormick, Barnes McCormick. Over here, it gives a pretty good estimate of static thrust. Another way is to get some company test data. And it looks typically like this. On the left, it's simply a graph of test data. The vertical axis is a ratio. These are coefficients, but it's a ratio how much thrust you get for how much power you put into it. And over here is the rest of the equation. So you stick your power in here, and it depends on propeller diameter. The horizontal axis here is the amount of power you're putting into the propeller or helicopter rotor. And you'll notice it drops as you go to the right. So if you feed a propeller more and more data, you get more thrust, but proportionally not quite as much. In other words, it's less efficient. Try to shove a whole bunch of power into a small propeller. And that's exactly what we found back here. That is this chart. Feed a whole bunch of power into a small rotor, you don't get proportionally much thrust. Okay, we're almost done here. Ducted fans. There's a lot of interest in ducted fans, and they do have some advantages. Sometimes people don't quite take into account the disadvantages, but the advantages are real. You have less tip losses. Propellers are kind of like wings. They generate lift, and out at the tip, the air goes around the corner, and you lose some of the thrust, and you pick up more drag. So by having a duct around the propeller, you constrain those losses. You don't have that air going around the tip. So you fix that problem. You can actually control velocity through the duct, and the flow contraction downstream, which hurts free propellers, can be controlled with this. So because of that, you get more efficiency from the same diameter propeller, and it's also safer. It's safer because you're not as likely to walk into it. It's also safer because if one of these blades breaks and comes off, it won't cut your ankles off, which appears to be a problem in some of the designs I've seen. So that's safer and more efficient, but the efficiency is mostly at low speeds or high disk loadings, high thrust loadings. Noise reduction. Yeah, if you put a shroud around it, a duct that's shrouded and maybe some kind of soundproofing, you can also reduce the noise, and that's a good thing. You see them a lot on blimps. You see them a lot on radio control models. Why don't you see them on real airplanes? Well, it gets worse as you go faster, and that's the bottom line. The drag of the duct gets worse and worse and worse, and there's pretty much nothing you can do about it. You also have to build these things very carefully. To get good efficiency, this gap here has to be really tight. And to make that tight, this whole structure has to be stiff, and it has to be attached very rigidly. So by the time you do all that, there's a weight penalty, a cost penalty, and a maintenance penalty. So this is kind of a rule of thumb, but it's probably true. Certainly by 100 knots, any faster than that, it's probably not worth having, and maybe even 50 knots if you fully take everything into account. But for this project, this competition, we're not flying faster than 50 knots. So maybe it is an advantage. Down here is an equation from Holman to give you the rough answer. Again, if you go to other sources, you'll find rather detailed ways of calculating the actual thrust you get from a ducted fan. If you're flying vertically in anything like a rotor, a single rotor, you have some serious problems. One of them is the torque. The rotor is going to torque you around the wrong way, so we typically put a tail rotor, which is blowing the opposite direction to stop the torque. That tail rotor needs power, and there's a long shaft and there's gearing and all sorts of things that lose power. When you're all done, you lose something like 15% of your engine power just counteracting this torque. So you can imagine people have tried to come up with alternatives, and you can see some of them on the chart here. This rotor, though, it allows you to control the whole vehicle because you can have it change lift as it goes around. So you can set it so you get more lift on this side and less lift on this side. And that's actually how we control these things in pitch and in roll. In fact, that's the difference between a rotor and a propeller, really. A rotor allows you to do that. A propeller, it's the same thrust all the way around. Okay, well, how else can we control the torque? Well, coaxial, these are going in opposite directions. That would work. All the others are also going in opposite directions, so they also counteract the torque. And with these arrangements, tandem and side by side, you can also get better control. Here you can get good pitch control by changing the power, and here you can get good roll control by changing the power. But you still have to control the opposite. So you still need to use the rotor for roll control here, and you need to use the rotor for pitch control here unless you put a separate surface here. So there's something that has come along fairly recently. You've all seen it because you can buy these at every mall now, and that's a quadcopter. And these are kind of neat because if you set it up right with these going in opposite directions, you can control roll, pitch, and yaw just by feeding different amounts of power to these things. And electric motors are particularly good at that. So this actually, it enables electric helicopters, and the fact that it's electric allows you to do this. So it's kind of neat. And you see this in a lot of the vehicles that people are trying to make for small manned vehicles like this project. Okay, almost done here. A couple more things. We have gone through this initial configuration. We're at the point now where we need to make a layout. And let me talk just a little bit about that initial layout, and then I'll be done. And this shows a typical initial configuration layout. This is actually a project I did many years ago. It helped me earn the reputation as that young crazy guy in advanced design, but it was a single seat, pure jet designed for an Army mission, which we never convinced the Army they wanted to do. I don't know if they were laughing or scared to death of it, or maybe a little bit of both. But anyway, we had fun. But what I want to show you, though, is what an initial design layout looks like. And of course, this is done in a CAD system. What does it look like? Well, you've got all the components, internal components, passenger, landing gear, all that kind of stuff, engine, payload, whatever that might be, landing gear basic geometry. You've got the overall arrangement, wings and tails and stuff like that. OML stands for outer mold line. You need a reasonably good external definition. It doesn't have to be perfect. And given the fact that we're going to change it so often, we're going to iterate, it's a good idea if you're not stuck with a CAD system that forces you to make it perfect. That's kind of a negative work because you don't really need a perfect geometry now. But later you have to get perfect geometry, of course. Fuselage, nacelles, all those sorts of things have to be there. Major structure, systems, fuel tanks, all that stuff has to be in this initial layout. And then you take this layout, you run all the analysis you can on it, you get all the experts to look at it, and you make the second layout. So you iterate through the design process. All right, well, that's about what I wanted to say. So we can take some questions now. I will throw this chart up there as a little bit of advertising. Okay, got to do that. Okay, I'll back up. Okay, questions? I'm not hearing anything.
Hey, Dan, thank you for the slides there. That was great. So a couple of questions. So if anybody does have questions, you can go ahead and put them in the Q&A button here in your Zoom webinar interface, and we'll ask a couple to Dan here with the few minutes we have left. So first question, is there any particular design or optimization software that you'd recommend people use?
Well, that's kind of a loaded question because I actually have my own RDS aircraft design software, which does include optimization. Other people's software, I don't have any particular names to give you. There are other packages out there. And of course, a lot of people develop their own, especially for optimization. There are some optimization frameworks that you can plug particular analysis into. It's kind of becoming a commercial commodity now, but I'm not familiar with a package out there that's really ready to go and sort of push buttons and get the right answers out other than my own software, and that's tailored to the types of things that I do.
Great. And without endorsing a particular one, is there something that you'd look for in a software if you were out there looking around for a couple different ones?
Well, as I mentioned, a CAD system should allow you to put a design together quickly, not forcing you to make it perfect. Because you want to be able to knock a quick design together in half a day to a day, and then go through and do a lot of analysis from that. You want a good interface to analysis, and it's good to have some built-in classical analysis that you can get some pretty good answers real quick. I think if you're immediately going to computational fluid dynamics for the aerodynamics, I think maybe that's a bit non-productive. I think you want some quick answers before that. So those are the types of things I'd look for. A CAD system that lets you quickly iterate, and a good link to some quick analysis methods.
Great, thanks. Here's a fun question for you. So you used both the word aircraft and you also used the word vehicle. Do you see a shift happening in that vocabulary to vehicle? And is that something more recent? Do you have any sort of fun thoughts about the vocabulary there?
Oh, I always say aircraft, except I do more and more projects with spacecraft and blimps and all sorts of crazy things. So you try to come up with generic terminology, but vehicle is kind of boring sounding. So I don't know what to say. I just say something different every time.
Sounds good. Great. We had a couple people asking about the webinar recording. I just want to mention for everybody that it will be made available later. So if you missed it today, you'll be able to see it later. And then question about, do you think that that electric propulsion modifies the classic weight regressions that you spoke about?
Oh, yeah, definitely. It's just different. The numbers are different. The whole propulsion system is different. The installation, the structure around it. It's not hugely different. It's not like completely different. Oh, gee, we never saw that before. But definitely changed and adjusted. And as we do more and more electric aircraft, we'll get more and more good feeling for how those numbers should change. As of now, if we don't have a lot of information on previous electric airplanes, we just have to take the classic airplanes and scratch our heads and modify it as we see fit.
Great. Let's see. So you mentioned a little bit the size constraints for the competition, and a little bit about sort of the difficulties that presents in terms of some of the graphs that you showed, and there not being lots of data in those particular spaces on those graphs. Do you have any sort of thoughts about innovations or things you're excited to see as people approach those parts of the graphs?
I'm sorry, I don't really understand the question. The graphs that I showed are mostly statistics on previous types of aircraft. And if you have an aircraft that's completely different, then you have to somehow calibrate the graph. Usually you'll find that even for a rather different type of vehicle, that the trend lines are about right. So the slope, the angle going down is usually right. So sometimes you can adjust it by quickly calculating a single data point, like coming up with a design roughly estimating what the empty weight should be, and then sliding the whole graph up or down until it passes through that. So usually the slopes are about right even for other classes of vehicles. Mathematically, what I'm saying is that often the constants are off, but the exponents are usually approximately correct. So that's what you do when you don't have any data from a previous kind of vehicle.
Great, thanks. And then a question about bladeless aircraft, things like air multipliers or something akin to like the Dyson fan. Do you have any thoughts on that?
Well, I mentioned before that you don't want to have a vehicle that literally can't take off if the thrust to weight isn't high enough. And the only recent example I can think of is the XF12, which was actually developed by Rockwell, NASA, Air Force, no, NASA, Navy, and Rockwell. And it literally couldn't fly. And the reason it couldn't fly is because it had one of these multiplier schemes using viscous entrainment, and it didn't work as well as they thought it would. So watch out for laboratory results, because it worked in the laboratory.
Great. And then another question about the difference between micro or smaller aircraft and downwash. Do smaller aircraft get caught in their own downwash like larger helicopters do?
Yes, they do. I wouldn't quite phrase it caught in their own downwash. That sounds too extreme, but there definitely is an effect of the wind blowing down from your own power, whatever you're using to stay up, and that blows down. It does push down on you, and you do have the effect where it hits the ground and then reflects upwards. There's a YouTube video many people have seen that shows a young woman flying one of these things off the side of a cliff, and she's zooming around over the water. It's a really neat video. If you look at it carefully, when she first turns it on, she doesn't have a helmet on, which is not the greatest idea, but she has long hair, and when she first turns it on, her long hair blows straight up. And that's exactly what this is. This is that fountain of multiple fans blowing down. They meet in the middle, and the air blows up. So perhaps they could put some kind of plate down there and catch some of that lift.
Great. And say you already have a design in mind. What's the best way to use the equations?
Well, it depends so much on the design that you have in mind. Of course, we don't want to reinvent the wheel, so whatever you're trying to do, go into the known state of the art, the textbooks, the known ways of doing things, and see which ones apply. Use the ones that apply as much as possible. When you get to something that simply isn't like anything done before, well, you got to make up a method. And then it's important to sort of document and try to figure out what adjustments you made so that somebody can replicate it later. It's also a good idea to show it to other people. You know, hey, this is crazy. It isn't like anything I saw before, like the picture on the screen right now. I'm going to handle it by this kind of an adjustment. A good example is for this one, the big rotors out there actually help a little bit with the lift-to-drag ratio. Well, the right answer comes from wind tunnel test or very expensive computational fluid dynamics. And I didn't have access to either. So I had to come up with a rough adjustment. So I scratched my head and came up with something, and I showed it to some other people, and they said, oh, probably as close as anybody's going to get now. And that's what I used. And then later we ran CFD on it.
Great. And then you mentioned additional power and thrust are required for control. How do you determine if a design has sufficient control?
Oh boy. Well, you know, with big companies, the right way is a whole bunch of data that takes a long time to get, and you put it in a very detailed 6 degree of freedom dynamic simulation program. And that's not an easy thing to do. For something like this, I think a lot of people will make some educated guesses and build it and start testing it, and see how it is, and go back and change it if it doesn't work well enough. You might try subscale, or might just build the full size one and use that remote control with the dummy rather than put yourself in it the first couple of flights.
Great. And then you showed a slide that had a number of different pictures of helicopters with multiple props on them.
Yeah.
Somebody's just asking how big a difference having those contra-rotating props makes from a single prop.
Well, if you look at all the helicopters that have ever been built and successfully produced, most of them do have a single rotor with a tail rotor. And there's probably pretty good reasons for that. I think for some special applications, some of the more innovative ones might be superior. But a lot of times in aircraft design, I hate to say it, but a lot of times the boring, obvious answer that everybody's done before often is the best answer. So at least as you're doing your trade studies, always look at the boring, obvious approach. Usually wins, but not always.
Sure. And then perhaps last question here, but somebody asked if you could provide just a brief explanation about blade element theory.
Blade element theory, brief explanation. Okay, well, you take the blade, you take I don't happen to have one, I got this thing, it looks kind of like a blade, and it's spinning around like this, and you break it into strips this way, and for each strip this way, try to determine its actual angle of attack as it goes around. You have to take into account the rotational speed. You have to take into account how fast you're going. You have to take into account the air that you're pulling into the propeller, which actually changes the angle of attack. And then you finally can find the angle of attack at each element. You can then calculate the lift and drag. You have to calculate the directions of those, and then use vector algebra and add them all up in the torque direction and in the thrust direction. And whoever asked for that, brief explanation. There you go. That's as brief as it gets.
Great. Sounds good.
Is that a test?
Yeah, I think you may have passed. That's great. One final question. So do you think that the dynamics and control for subscale aircraft translate well enough to full scale?
No, but sometimes it's all you've got. There are equations that will let you change the weights and the mass distribution in a way that properly scales, and it's slightly complicated mathematics. I got them around somewhere. But the problem with that is if you change them so that the dynamic scaling is correct, usually the vehicle is too heavy to fly. So if you do a subscale test, just be very careful and realize the full scale one may not fly as the subscale one does, but a lot of times it's all we have to go on. So we do that. Just be careful when you fly the full scale one. Make sure you don't kill your dummy.
Great, thanks. And
hopefully
with that,
partner.
I'm sorry?
I say, hopefully the dummy isn't what you call your partner. Hopefully it's an actual non-human dummy.
Great. Sounds good. Thank you so much, Dan. And with that, I'll pass it back over to Gwen for just a couple of closing remarks.
Well, Dr. Raymer, thank you so very much for a wonderful master lecture. We truly appreciate your insight and your expertise. There are so many different ways to solve the Go Fly challenge, and we truly appreciate your discussion on some of them. If you, to all of the innovators out there, if you already have a design in mind, these discussion points will help you to understand and predict your performance. We look forward to another 2 years of master lectures, and we're so pleased that you all have joined us, and a very special thank you once again to Dr. Dan Raymer.
Great. Thank you so much.